extra time. Oops. All right, let's see how to answer today's quiz. So we are supposed now to find the charge. And, well, actually 4 different values of charge. This is what we are supposed to find in order to answer properly the quiz. Now, this system of capacitors is a system of capacitors connected in series. Well, if they are in series, it means that whatever charge enters this capacitor, it has to enter that capacitor. So if this capacitor has contains charge of 1 microcoulomb, which means actually that 1 microcoulomb is millicoulomb is transferred from one side to the other side. So let's say that 1 millicoulomb is on the left-hand side. The charge on the right-hand side will be automatically minus 1 millicoulomb. Well, where that excess charge, what happened with that excess charge? It was pushed to this plate. So this plate will have charge of 1 millicoulomb. The other will have minus 1 millicoulomb. So the second capacitor is also charged with a charge of 1 millicoulomb. Now, if we look at this entire system, we had charge of 1 millicoulomb on the left-hand side of the system, and we have minus 1 millicoulomb on the right-hand side of the system, which means that the charge on the entire system is also 1 millicoulomb. So, for connection in series, all three charges are equal on the first capacitor, on the second capacitor, and on the 2 capacitors together on the system. All right, now let's take a look at this system. Here, I can recognize that potential on this side of the top capacitor is the same as potential on the left-hand side of the bottom capacitor, and the potential on the right-hand side of the top capacitor is the same as the on the right-hand side of the bottom capacitors. These 2 capacitors are connected in parallel, but since we figured out that we have the same potential difference across this capacitor and across this capacitor, well then, since charge stored on a capacitor is equal to capacitance multiplied by potential difference, so if potential differences are equal, and one capacitor has twice capacitance of the first capacitor, then charge on the second capacitor is 2 millicoulombs. Now, let's see how much charge is transferred from one side of the system to the other side of the system. So let's say that we have this 1 microcoulomb on this side, millicoulomb. Then it will be minus 1 millicoulomb on the right-hand side, on the top capacitor. And on the bottom capacitor, you will have 2 millicoulombs and minus 2 millicoulombs. So on the left-hand side, we have 3 millicoulombs. On the right-hand side, we have minus 3 millicoulombs. So the charge stored on this entire system is 3 millicoulombs. Let me modify this quiz, and I want now to discuss something else. How about if we find out voltages across the capacitors? What's the potential difference across each capacitor? All right. So, product of capacitance and potential difference should give me charge. So, what potential difference will satisfy this condition? 1 volt. So, potential difference across the top capacitor is 1 volt. What's potential difference across the second capacitor, therefore? Also 1 volt. We figured out that potentials on the sides are equal, corresponding sides are equal, therefore potential differences must be equal as well. So it will be 1 volt, 1 volt. Now, how about here? Well, what's potential difference across this capacitor? Well, we can figure out exactly the same way as in the first case. So this charge should be equal this capacitance multiplied by potential difference. So it must be 1 volt also. So potential difference across this capacitor is 1 volt. Now we figured out that charge on this capacitor must be the same as this one. So potential difference, so we have 1 millicoulomb on the second capacitor. Since capacitance is 2 microfarads, potential difference across the second capacitor is 1/2 of a volt. Now there will be a problem, because potential difference across the entire system should be therefore 1.5 volts or 1/2 a volt. Yeah, because it depends now on polarity. If I have potential here higher than there, so assuming the potential here is higher than potential there, so this potential minus this potential will be 1 volt. Now, if this potential is higher than this one by 1/2 a volt, then potential difference across the system is going to be 1/2 a volt. However, if potential difference on the left-hand side is higher than potential difference on the right-hand side, then it will be 1.5 volts. So who votes? Let's vote. Who thinks that potential difference across entire system is 1.5 volts? Who thinks that this is 1/2 a volt? All right, I assume that the rest don't have who doesn't have an opinion? What are the other options? All right, let's now see. The correct answer is 1.5 volts. And let's see for the reason. All right, so in order to have potential difference between this point and this point to be 1 volt, yes, so this potential minus this potential, I want to be 1 volt. How the capacitor is charged? This 1 microcoulomb is on the left-hand side or on the right-hand side? And minus 1, I have to change probably to microcoulombs, millicoulombs. Why millicoulomb? This charge of 1 millicoulomb is going to be on the left-hand side or on the right-hand side. And automatically minus 1 millicoulomb will be on the other side. So if potential here is higher than potential there, show me with your hand. Potential charge 1 millicoulomb will be this way or that way. Show me. I mean, obviously it's not that way. I gave only choices to the left and to the right, so don't show forward. All right, Chris, why do you think the potential here is going to be, charge here is going to be 1 millicoulomb and here will be minus 1 millicoulomb?
Well, isn't it supposed to be the charges are opposite on opposite sides? Well,
yes, but I can have it 2 ways. Let me go to the whiteboard let's talk about this on the whiteboard. We have 2 possibilities. This is just that one capacitor, 1 millifarad capacitor. Now we can have it charged 1 millicoulomb here and minus 1 millicoulomb there, or minus 1 millicoulomb here and 1 millicoulomb there. Now potential difference is 1 volt, right? No matter what. Because when I say potential difference is 1 millivolt, I'm ambiguous really. Which potential difference is 1 volt? Let's say VA, VB, VA, VB. Over here, which potential difference is 1 volts. And the problem which you have at this moment is that you learned inaccurately the relationship Q equals CV. You don't know what V is, or which V to take. And so let's recall the drawing which we had when we defined capacitance, when we introduced capacitor. Yeah, on the drawing I had Q here, minus Q here, V1 and V2. Yeah, so Q is equal to C times potential difference. Which one? V1 minus V2 or V2 minus V1? Who believes that it is V1 minus V2? Who believes that it is V2 minus V1? Correct answer is V1 minus V2. It's possible that the formula which I had was V2 minus V1, but you have to relate to the drawing. You should subtract from the potential on which charge is Q, potential on with that other one. Yeah, I could for example start with this one. Yeah, I think that now this is my Q. As I will write minus Q equals C, and then I have to be consistent. Now it will be V2 minus V1. Look that those two formulas are identical. You just have to remember how to select the quantities. Now, this is just the first electrical element which we are discussing. We will discuss more, and we will, in a circuit, we will have, in this class probably we will never have more than 5. But in a TV set, you have 50 elements. And if at each element you will think, well, it's this potential difference or the other potential difference. Even if you bet with probability, let's say 90%, for those 50 elements, what is the probability that you will make an error? 0.9 to the power of 50, which is a pretty small number. So practically I can bet that you will make it wrong. You will confuse it. Even with 5, if you make with probability 0.9, it's already quite a low probability. It is 0.9 to the power of 5. If at every element you bet 50, with 50-50, well, 90-10 probability. But most likely you will even bet with 50-50. All right. So consistently with this, how I did it over here. Well, if I take, well, 1 microcoulomb, so millicoulomb, so 1 millicoulomb should be equal to 1 millifarad multiplied by this potential minus this potential. All right, so now consistently with that, if we come back to the drawing, so if 1 millicoulomb is on the left-hand side, which means potential here is higher than potential there, and we will have 1 millicoulomb on the left-hand side of the second capacitor, which means that potential here is higher than potential there. So potential difference will be 1.5 volts. All right, so this will be enough for analysis of this circuit. Oh, these are the answers. And I want now to talk about the next subject, because so far we had situations in which, well, we delivered somehow charges and they were in place. Now we will be talking about what happens with charged particles move. They carry charge from one part of a space to another part of a space. And that phenomenon of transferring charge from one side of the space to another side of the space is referred to as electric current, more precisely electric conduction current. Because in the future we will learn about a different type of current which is associated with changes in the electric field. That kind of current is referred to as displacement current. But today we are going to talk about conduction current, which is associated with charge carried by charged particles. Remember, the charge cannot move on its own. It has to be carried by particles. So particles have to move. There is no some kind of extra fluid in bodies which is charged and it's non-material. Charge is associated with particles, so current can flow. In other words, charge can be transported from one side to another side only one way. Charged particles have to be rearranged. You will be somewhat confused with the word current, because current has a double meaning. Well, first of all, it is the transport of charge. So if we have traveling particles, charged particles through the space, we have current associated with that space. That the set of moving particles form an electric current, and it can be current can be created or caused by positively charged particles. So, for example, protons. We can have a beam of protons flying through space, and that beam of protons flying through space forms an electric current. We can have negatively charged particles, like electrons, for example. So, and actually, in the case, I mean, when we wouldn't, from outside, we would not be even easily, I mean, if we just see how the object becomes charged, we wouldn't be able to say if it is associated with the motion of electrons or protons. Both will charge the same way, because see what will happen if, let's say, in a neutral body, positively charged particles move to the right-hand side. So right-hand side becomes positively charged, left-hand side becomes negatively charged. Now don't think about protons, think what will happen if electrons move from the left-hand side to from the right-hand side to the left-hand side. Again, the right-hand side will become positively charged, left-hand side is going to be negatively charged. Now, according to the general agreement, we say that the direction in which the current flow is the direction in which the positive charge would be transferred. So, for example, in the case which you see in this figure, well, let's start with this one. We have current, electrical current flowing through the right or to the left. Who votes that it will be to the right? Who thinks that it will be to the left? Those who think that it's to the right, you are correct. Positively charged particles, you have to follow which way the positive charge is moving. Now, how about electrons? This one. So who believes that the current is flowing to the right? Who believes that it's flowing to the left? Those of you who said that it's flowing to the right, you are correct. Positive charge is transferred from the left-hand side to the right-hand side, although it hasn't been even moved. But the right-hand side became positively charged. All right. So this is one meaning of word current. Now the second one, okay. The second one is a physical quantity. Yeah, because the first meaning, it was a phenomenon. The second one is a physical quantity, which describes electric current. So what quantity I'm introducing to describe electric current? Shout. A what? A what? No, amperes are the units of that physical quantity. But what is the name of the quantity which describes electric current? Read the screen.
Electric current?
A what?
Electric current?
Electric current. Correct. Yes, so electric current, physical quantity, describes electric current, a phenomenon. It could be confusing, but this is subtlety of the language. Actually, a lot of languages. In Polish, is the same way. Phenomenon and the quantity has the same name. And I wonder if there is a language in, probably, I don't know. I don't know if there is a language in which actually there is a distinction between the quantity and the phenomenon. All right, now let's comprehend the quantity. So by definition, electric current is the rate at which charge is being transferred through the surface. Now, whenever we speak about electric current quantity, we have to associate it with a surface. We don't have just electric current flowing somewhere. It has always to be through a surface. Even if you don't say that it is electric current through a surface, you have to keep it in mind that it's electric current through a particular surface. Quite often you will say electric current in a wire. When you say electric current in a wire, you have to think about a certain surface in that wire, and we'll talk about it in the future. All right, Adam recognized, and probably he heard already, word amperes or ampere. Ampere is a unit of electric current, SI unit of electric current. And we are still not in a position to I cannot at this moment tell you what is the standard for 1 ampere, but 1 ampere has a standard, like 1 kilogram, for example, has a standard. 1 second has a standard. 1 ampere has a standard. Or 1 second also has a, oh, I said that. 1 second has a standard. Well, however, if we comprehend ampere, then Coulomb is defined actually as a charge which crosses a surface in 1 second when the current flowing through that surface is 1 ampere. So Coulomb is a secondary unit from ampere. First we have to have a standard for ampere. When we understand ampere and second, Coulomb can be introduced. So now I at least supplemented the unit of charge. All right. Oh, before I go to this one, I want to point out something else about it. Now, note that current, let's think about what kind of quantity is it, current a vector quantity or scalar quantity? Let's start with this. Charge. Charge is a scalar quantity or vector quantity. Who believes that it's a scalar quantity? Majority of you recognizes the charge is a scalar quantity, and it's correct. How about time? Time is a scalar quantity, or who believes that it's a scalar quantity? Time. Also scalar quantity. Both are represented by numbers, not by vectors. All right. So now this derivative, which you can really look at this as a quotient. So if I take a quotient of 2 scalar quantities, I'm going to get the scalar quantity or vector quantity. Who believes that it's a scalar quantity? Who believes that it's a vector quantity? All right. If we take quotient of scalar quantities, we will get a scalar quantity. Quotient of scalar quantities is a scalar quantity. All right. Now, if I look at these protons traveling, or ions traveling to the right, which direction the current flows? To the right, right? Well, so there is something confusing, right? Because you remember that one of the, and I bet that you believe that vector quantity is a quantity which has magnitude and direction. Well, I can assign direction to that flow. How come that current is not a vector? Well, think about it. Well, yes, we always assign direction in a certain artificial way. Yeah, when I walk, we choose the direction which I'm heading to be the direction of my velocity. Yeah, it's also artificial. I can make it to the left. Yeah, so the direction of my velocity is to the left always. We don't do it because it's more complicated, not mentioning that it would work only on a plane. However, for example, for rotations, we use right-hand rule. So we have another trick how to assign direction. If we recognize that something has direction, we can find out a way to assign direction, and it is not unique. We could reverse. I could say that whenever I walk that way, I have the velocity is the other way, and that one even would work in 3 dimensions. It's not particularly intuitive, though. Well, yeah, because over here we associated. This direction refers to the direction of the flow. It's a different current than this one. This is a physical quantity which describes that. That motion over here has the direction. The quantity doesn't. However, we have a physical quantity which incorporates also the directional property of that flow. But before we comprehend, that quantity is called current density. Current density is a vector quantity, but their current density requires a concept of drift velocity, which would be something you can think about drift velocity like a velocity of a crowd. Yeah, if you have a crowd of people, St. Patrick's Parade, that crowd of people moves with certain velocity, despite everybody moves kind of randomly. By definition, drift velocity, in order to determine drift velocity, I have to consider a relatively small space and find what is the average velocity of the objects within that space. So, for example, in a St. Patrick's Parade, we could assign drift velocity to the location where you are by taking your velocity and the people around you. So let's say 5 people all together, calculate average velocity of those 5 people, and it will be drift velocity at your location. At some other part, so in the other part, you can find out that people over there move differently, so the drift velocity at that location is going to be different. How about if we take a look at the simulation to see? So think about that these blue dots are electrons, and I miss electrons over here, I miss electrons behind, but now this simulation really shows how electrons will move in one of the models. So they will move until they are scattered by some kind of center due to collision. So if they collide with some atom, they will stop. Now, but let's say that I apply electric field up, so these electrons are pushed downward. So between the collisions, they will move with constant acceleration. All right, and, well, run here. This is how they move. You can recognize this entire crowd is moving forward. But now look at the path of an individual. Yeah, an individual is moving, because sometimes it was moving even backwards. Yeah, like over here, it moved backwards quite a lot. But as the crowd, this entire set moved downward. And note actually that it even looked like this crowd is moving almost with a constant velocity. All right, so let's go back now to the. So I hope that this simulation well gives you intuition now about drift velocity. All right, now this, what the drift velocity does is that the center of charge enclosed in that volume moves with the drift velocity. So really this is the rate at which charge is being transferred, on the total charge is being transferred. Now, center of a charge has is defined in a way very similar to center of mass. So let's now calculate the rate at which center of mass moves, or the drift, the velocity with which center of mass is traveling. So, according to the definition of velocity, I have to take time derivative of that center of charge. And center of charge, I said that it is defined in a similar way like center of mass. So for each particle, I have to multiply position of the particle by its charge, and then divide by the sum by the total charge of the system. It's the same. Recognize that it's very similar like center of mass. For center of mass, I had to multiply mass of each particle by its position, add the products, and divide by the total mass of the system. All right. Now the rest is really just math. So I can recognize that I mean, I consider a certain number of particles. I have identical particles over here, so I'm just thinking at what rate center of charge of electrons is moving. So they are identical particles. I can take this Q outside. It will cancel with that other Q, and here I will be left. Oh, and derivative of a sum is equal to sum of derivatives. So this is a mathematical step. I take constants in front of the derivative. I took this constant in front of the sum, and then moved derivative as far to the right as possible. And that further it is that I have to differentiate position of individual particle. Now, what is that? Derivative of position of ith particle with respect to time. This is of a particle. Which one? The ith particles. Correct. So this is velocity of ith particle. Well, which I have over here. Yeah, velocity of. So this is velocity of ith particle. Q and Q cancel. So I have 1 over n. Oops. Which means that I got drift velocity. Now, when we understand concept of drift velocity, I can introduce the second physical quantity which describes electric current. Electric current as the phenomenon. What was the first quantity? Electric current. Correct. Electric current. We use electric current to describe electric current. Now we can use current density to describe electric current. And current density is a vector quantity. It is associated with the drift velocity of the charge carriers. So by definition, current density is equal to the number of particles per unit volume times charge of the particles times drift velocity of those particles. Number of particles per unit volume is referred to also as concentrations of the particles. Why don't we say it loudly? Concentration of the particles. Say it. Concentrations of the particles, correct. And let's say it loudly. What is this quantity? Current density, correct. Well, and current density is a vector quantity which describes what? Electric current, correct. And which electric current? The phenomenon or the quantity? The phenomenon, correct. It describes the phenomenon. Now electric current quantity describes what? Electric current, the phenomenon, right? Well, we have two quantities which describe the same thing, which means that they have to be related. And, well, let's take a look at the relationship. I mean, the relationship, let's start with this, with bringing up the relationship. Current through a surface is always equal to the flux of current density. And we already are very familiar with the concept of flux, right? All right. Well, just to exercise this, I want now to verify that relationship. So, how about if we take a surface, let's say that we know that we are able, well, and for this surface, let's try to relate current density at each point of that surface with the current flowing through this surface. Remember that current is always associated with the surface. We don't have current in a point. We have current density at a point. We don't have current at a point. Current is always through a surface. So tomorrow, I always want to hear current through what? Through what surface? You will have to identify what surface we are talking about. All right. Well, in order to find out current through the surface, I have to determine what? The rate at which charge is being transferred through this. So, how about if I think that there are particles, charged particles, crossing this surface, like that, and estimate what is the value of the current. So, in order to do this, I will, so let's say that let's start at this point. Consider a small surface, a differential surface with an orientation, the vertical orientation, and drift velocity of the particles traveling through the surface is marked like that. I did not mark the particles because they will fog the picture. But you have to imagine that there are particles crossing the surface, and on average, particles crossing this tiny surface move in this direction, making angle theta with the surface vector, or theta with the direction normal to that surface. All right, so now I'll find out how much charge is passing through this differential part. From that, I can add these values for all pieces, and that way I will get the charge passing through the entire surface. So right now I want to concentrate on the charge passing just through this small surface. I will use symbol d small q. So how d small q is related to d capital Q? I have to add, right? dq is just through a tiny fragment of the surface. I have to add over all tiny parts of that surface to get the capital dq, because capital dq is charged through the passing through the entire surface in time dt. Small dq is charge passing through just one differential fragment of that surface. All right, so I will now try to relate this charge to drift velocity. Well, in time dt, let's say that the concentration of particles at that location is n, and at time dt, particles which are in in this parallelepiped will cross the surface. Now this parallelepiped is not exactly random. It is that its edge is parallel to the drift velocity. So if a particle is inside in time dt, it is going to cross it. Yeah, if particle is somewhere far away, that it won't cross. So let's say imagine ourselves. I mean, think about yourselves and think that that you are running that way. Let's say 5 meters per second. Well, that way. All right. Let's make 10 meters per second. Now, who is going to cross the door? Let's say that distance between the door and Vincent is 10 meters. So is Vincent going to cross the door? I mean, let's say that it's 9 meters. Yeah, from door to Vincent it's 9 meters. Vincent, will you cross the door in 1 second?
No.
Why not?
Because
you are too far, right? Because you are 9 meters away from the door, and you move with speed 10 meters per second.
Oh, then I wouldn't.
Then you will, right? You have enough time to cross the door. Now, how about you? Will you cross the door? Yes. Adam, how about you? No, you wouldn't. You have shown me the direction of your velocity. I said that you will be moving that way. But you can think that actually when drift velocity is such a quantity that since it is average, you can think like we all move with drift velocity. So Adam will not cross the door. Why not? Because the direction is wrong. Yeah, he is somewhere over here. He has no way to cross this surface moving in this direction. All right, so Adam will miss because he is at the wrong location. Now, how about Chris? Chris, are you going to hit the door?
Going in the right direction of my extension.
Chris is going in the right direction. However, he is more than 10 meters away from the door, right? So he will not reach the door on time. Yeah, so he is behind the bottom base of the parallelepiped. Can you understand that? Yeah, only those particles which are in this parallelepiped are going to cross the surface. So I can evaluate, therefore, the charge, that it will be the concentration of the particles, number of particles per unit volume, multiplied by the volume of this parallelepiped, and multiplied by the charge. All right, now that volume over here is determined by this, what is this distance here? And this distance is magnitude of drift velocity multiplied by time. Now, this is not a block, so the angle here is not 90 degrees, it is a slant angle. So we have to incorporate only a component perpendicular, so we have to multiply it by cosine of that angle theta in order to find the volume. So how did I write it now? So I copied concentration and charge of individual particle. Now, this is area of the base, this is the length of the side, and this is cosine of that angle over here. Now, if I take out, if I combine concentration, charge of individual particles, and drift velocity, or probably, or magnitude. Oh no, before doing this, I can recognize something else, that magnitude of the dA, which is area, and it's at the same time magnitude of this vector. Yeah, recall that surface vector is assigned in such a way that its magnitude is equal to the area. So here I have magnitude of the surface vector. This is magnitude of drift velocity. And here I have cosine of the angle between drift velocity and the surface vector. What do I really have here? Magnitude of one vector times magnitude of the second vector times cosine of the angle between them. It's a dot product between these two vectors, correct? So see, here I have a scalar product of drift velocity and the surface vector. The dt stayed over there, and I had it before. So now I can recognize that concentration times charge times drift velocity is equal to the current density. All right, so what have we found here? A charge which is passing through that red surface. In order to find out current through this entire surface, I have to add it over all pieces. Right? So I have to integrate over the surface the dq which I just found. And this dt is irrelevant to the segment, so I can take it in front. And from this, I can find out now what is the value of the current flowing through the surface, because current flowing through the surface is charge transferred through the surface in time dt divided by time dt, which means that current through the surface is equal to the flux of the current density over the same surface. And I think that this will be a right place to end the lecture. So thank you very much, and see you tomorrow.